Welcome to Sri Learning Academy. Let's simplify multithreading in Linux and Windows. The idea of multithreading exists in both Linux and Windows, but the way each operating system implements and manages threads is quite different in practice. Today, we will focus on how Linux and Windows actually handle threads at the operating system level and what that means in real systems. Let us start with Linux. In Linux, threads are implemented in a very interesting way. Internally, Linux does not treat threads and processes as completely different things. Instead, Linux uses a unified concept where both processes and threads are represented as tasks. These tasks are created using a system call called clone. Depending on the flags passed to clone, the new task may share memory, file descriptors, signal handlers, or other resources with its parent. When most of these resources are shared, the task behaves like a thread. When they are not shared, it behaves like a traditional process. This design choice makes Linux very flexible. From the scheduler's point of view, every runnable entity is just a task. Whether it is a process or a thread does not really matter. Each task gets its own entry in the scheduler and competes for CPU time just like any other task. This is often described as the one-to-one threading model, where each user-level thread maps directly to a kernel-level task. Because of this, Linux can fully utilize multiple CPU cores. If a process creates 10 threads, Linux can schedule those 10 threads on different cores at the same time. Now think about a simple example. Suppose you are writing a server application on Linux that handles client requests. Each client request is handled by a separate thread. If your system has 8 CPU cores, Linux can run up to 8 of those threads truly in parallel. If one thread blocks on disk I/O or network I/O, the scheduler can simply run another thread. This leads to very good responsiveness and scalability, which is one reason Linux is so popular for servers and cloud systems. Another important point in Linux is scheduling. Linux uses a scheduler known as the completely fair scheduler. The idea is to divide CPU time fairly among all runnable tasks. Threads do not get special treatment just because they belong to the same process. Each thread is scheduled independently. This means that a single process with many threads can consume a lot of CPU time if not controlled carefully. In practice, system administrators use tools like C groups to limit CPU usage when needed. Now let us switch to Windows and see how things differ. In Windows, threads are a core concept from the beginning. Windows was designed with threads as first-class citizens. A process in Windows is mainly a container for resources like memory and handles, while threads are the entities that actually execute code. Every Windows process has at least one thread, often called the primary thread. When a thread is created in Windows, it is always a kernel level thread. There is a strict one-to-one mapping between user threads and kernel threads. This is similar to modern Linux, but the internal design philosophy is different. Windows clearly separates processes and threads in its internal data structures. A process holds the address space and resources, and threads belong to that process and run within that address space. Scheduling in Windows is also different. Windows uses a priority-based preemptive scheduler. Each thread has a priority, and the scheduler always prefers higher priority threads. If a high priority thread becomes ready to run, it can preempt a low priority thread immediately. This design works very well for interactive systems. For example, when you click a button or move the mouse, the threads handling user input usually run at higher priority. This is why Windows desktops often feel very responsive. Consider an example here. Suppose you're copying a large file in the background on Windows, and at the same time you open the Start menu. Even though the file copy is CPU and disk intensive, the user interface remains responsive. This happens because the UI threads run at higher priority and preempt the background worker threads. Linux can also achieve similar behavior, but Windows does this very aggressively by design. Another key difference lies in thread synchronization and system calls. In Linux, thread related operations often use POSIX standards, such as pthreads. These are widely supported across Unix-like systems. Windows, on the other hand, provides its own native threading API. Concepts like critical sections, events, mutexes, and waitable objects are deeply integrated into the Windows kernel. This tight integration often makes synchronization operations very fast on Windows. However, portability becomes an issue. Code written using Windows threading APIs does not run natively on Linux. Similarly, POSIX thread-based code does not directly map to Windows without compatibility layers. This is why cross-platform applications often rely on higher-level libraries that hide these differences. One more practical difference shows up in how signals and thread termination are handled. Linux uses Unix-style signals, and signal delivery in multi-threaded programs can be tricky. Developers must carefully control which thread handles which signal. Windows does not use Unix signals. Instead, it relies on structured exception handling and other mechanisms. This often leads to different programming patterns when writing multi-threaded applications. From a performance perspective, both Linux and Windows are highly optimized for multi-threading today. In earlier years, Linux had an edge in server workloads, while Windows focused more on desktop responsiveness. Over time, both systems have borrowed ideas from each other. Modern Windows Server editions handle large numbers of threads very efficiently, and modern Linux desktops are highly responsive. So, which one is better? The honest answer is that it depends on the use case. For large scale servers, cloud platforms, and systems where fine grained control over resources is important, Linux is often preferred. Its unified task model and flexible scheduling make it very powerful. For desktop applications, enterprise environments, and systems where user experience and priority based responsiveness matter, Windows often shines. As we move forward to CPU scheduling and synchronization topics, you will see how these threading differences influence scheduling decisions, context switching costs, and synchronization problems. Multithreading is not just about creating threads. It is about how the operating system manages them under real workloads. Linux and Windows take different paths, but both aim for the same goal: efficient, responsive, and reliable execution of concurrent tasks. That is it for this video. See you in the next one.